And our last presentation before the break from Amnon Ptashek, Allotrope Foundation. We're very happy that Amnon was able to present because we're working with them. And the name of the talk is Leveraging HDF5 Infrastructure to Build an Interoperable and Contextualized Data in Pharma using semantic technologies. And I believe semantic was mentioned yesterday, that in HDF5 people are trying to store more than just raw data and organizing data. So with this, I give it to Amnon.
Hi, good morning, good afternoon. Do you see my screen?
Yes.
Okay, thanks. So hello again. My name is Amnon Ptashek, and I'm a member of the Allotrope product team. Just in an elevator pitch, Allotrope is a consortium of pharma companies. Most of the major pharma companies are members of our community, including some partner vendors. And in the following presentation, I will be talking how the ADF file format, Allotrope data framework file format, leverages the HDF5 infrastructure to create an interoperable and contextualized data infrastructure. I'll start with an RDF primer. It will be very short for those of you who are not familiar with the RDF graph. So RDF, the resource description framework, is a framework for expressing knowledge about resources. And resources can be anything, can be physical object, abstract concept, devices, people, anything. And we can visualize the knowledge as a connected graph. So you have nodes and arcs. And for those of you who are familiar with a knowledge graph, this is different from property graph. In property graph, the knowledge is in the nodes. In RDF graph, most of the knowledge is in the relationships, in the arcs. So typical RDF statement expresses relationship between two resources. For example, here, Bob is predicating the Mona Lisa. Bob is interested in the Mona Lisa. And the structure of the graph is a collection of triples, a set of triples with the structure of subject, predicate, object. So here, Bob is the subject, the object is the Mona Lisa, and is interesting in the Mona Lisa. The ability to have the same resource be in the object position in one triple and the subject position in another triple makes it possible to create the relationships in the graph and makes the graph very powerful. So from this graph, we see that Bob is interested in something that was created by Leonardo da Vinci. And the set of triple, the same set of triple that describe the graph is described here. So you can have it as a set of triple or as a visual graph. IRI, the International Resource Identifier, are used to identify resources uniquely. And object can be literal. For example, here, Bob's birthday is 1990. So it's the resource is a literal, the object. And there are a universal RDF vocabulary, such as, I'm giving you an example, a friend of a friend, for describing the domain of the resources. So a friend of a friend is a vocabulary for describing a social network. So we have a prefix, FOAF, a person knows a topic of interest. So Bob knows Alice. FOAF knows, Bob knows Alice. The RDF graph can be serialized using turtle syntax. So we see here the same graph in turtle syntax, and the turtle syntax is a self-describing syntax. So we see here the subject as the Mona Lisa, which is identified by the prefix Wikidata, WD, Wikidata, and the identifier, specific identifier for the Mona Lisa Q12418 as an identifier in the Wikidata. So the Mona Lisa subject was created by Leonardo da Vinci. And like SQL, for RDF graph, you have the Sparkle query language, the protocol in RDF query language to query RDF. So if we like to understand and to infer the people that are interested in the Mona Lisa, we created the following Sparkle query, select name, where name is the person, name is a person, and is interested in the Mona Lisa. So we get Bob as the inferred answer that is a person and is interested in the Mona Lisa. So now that we are expert in RDF, we can talk about the ADF file architecture and how it leverages the HDF5 file format. So we see here on the right side, we see the general structure of an ADF file. The ADF file contains several components, a data description, remember data description, this is where the semantic is going to be stored, data cubes, data package, and some auxiliary services for regulatory and compliance. And the entire infrastructure is encapsulated in HDF5 file format in a way that is a self-describing way. And the reason that I'm saying self-describing because the content of this data package and data cube is described in the metadata, very rich metadata, which is in the data description, as we will see in a moment. So the data description, which is again the metadata layer, is store the information in user-defined graphs. It stored it in RDF graph, so it's a set of triple. And it's based on Apache Jena. Apache Jena is the industry de facto semantic web framework to access a triple store. And typically the data description contains contextual metadata about the data cube, the information in the data cube, and the information in the data package. And typically for the pharmaceutical industry, it contains lab environment information such as result, sample, process, method, and so on. But in a generic manner, those file format, the ADF file format can be used in any domain and any industry. The data description, as we mentioned earlier, is utilizing the RDF technology, the semantic web technology for rich metadata and contextual information as opposed to simple HDF5 attribute. The data cube, the second layer, contains multi-dimensional arrays for data, specifically for the lab environment. We can contain measurement, result data, and in a multi-dimensional array. And the context of those data cubes is stored automatically within the data description. The data package is a general purpose virtual file storage system. It can optionally archive the same information like the data cube, but it ensures the data consistency and integrity. So you have the raw information data, the original native raw information data, and some of the process or the same data in multi-dimensional array. And again, all the metadata, very rich metadata about the information exists within the data description. So we see here the overall ADF API architecture. The underlying infrastructure is the HDF5 file format. And we have the data package on top, the data package API, the data cube API. We have the graph store that we will talk in a moment to store the triples on top of the HDF5. And we have the Apache Jena, the industry de facto API framework for semantic web. And all of this can get access through Java or C# library. So the ADF internal structure utilizes the HDF5 structure. So each of the layers, the three layers, the data description, data cube, and data description, and the auxiliary features are layered as a top level group in HDF5 file format. Like the HDF viewer, the one that you are familiar with, Allotrop has its own viewer, which is called the ADF Explorer. So we see a typical snapshot, a screenshot of the same data that are encapsulated within an HDF file, ADF file, sorry, and in exploring it with the HDF viewer and exploring it with the ADF Explorer. So again, it's the ADF Explorer versus the HDF viewer. We see the three layers, the data package, data description, and data cube in the HDF viewer, as well as in the ADF Explorer. And we'll see the comparison in a moment in a few of the layers. The data package is using a top-level data package group to hold the file system layer. Underneath the data package, folders are represented as HDF groups and files as HDF dataset. When you add a file to the data package, key metadata about individual files and folder are stored in the data description, the semantic information automatically with the ADF APIs, which means when you load a file, all the context, all the triples will be loaded automatically. We see an example, again, with the HDF viewer and the ADF Explorer of two Excel spreadsheets that are stored in the data package. You see how the data folder and the files, those spreadsheets are viewed in the HDF viewer and in the ADF Explorer. Until now, everything is very similar. The data cube of the ADF file intended to store a multi-dimensional array, and it consists on measurements, measures, dimensions, and scales. Measures are the observed value. It is, for example, we see here intensity. Dimensions are the control or the independent variable. So the X within a graph of X, Y, it's the X variable. For example, here it is time and wavelengths. And scales are value for the dimension. They are in the data description. All of those three are referenced in the data description to create a metadata to link them to the rest of the contextual information. We see here again comparison between the HDF viewer and the ADF Explorer. You see several data cubes, several multi-dimensional arrays, and you see the measurements in the HDF viewer and the ADF Explorer. Until now, things are very similar. The ADF Explorer has some additional features to view it in a three-dimensional graph, those multi-dimensional arrays. Now we're getting to the interesting part, which is the data description. So how to create a very rich, very powerful semantic layer within a HDF5 file format, which takes actually the HDF5 to the next level of contextual metadata, as opposed to simple attribute. So in order to store the information in a triple store, HDF5 doesn't have yet any native graph storage. So actually the ADF emulates this through a combination of a dictionary, a list of quads, actually quints, including a deletion flag, and multiple index listing for fast search. So looking at with the HDF viewer, the data description, the metadata is quite cryptic, which means you see the dictionary, you see the index for graph, subject, predicate, object, but you can't understand the triple store because it's encoded and emulated through the functionality of the triple store. So we'll see the same information with the ADF Explorer, the same graph store and the data description. So you see a list of a set of triples for as a metadata, and you see the graph that the RDF graph that represented the same information of those group of triples. So now that we are already expert in ADF file, I can go into the AFO, the ontology, and the models. How do we actually create interoperability using the ADF file. So you see here an example of a chromatography process, and you see just a sub-graph of the total RDF graph. It's a mobile phase of chromatography. We are using, in the process of modeling data, we have the taxonomy, the Allotrope Foundation taxonomy, which formalizes an hierarchical relationship of terms, and I will go through it in a moment. And we have the ontology, which provide a standard for the vocabulary and the semantic model representation. So we'll start from terminology. To create interoperability, you need a vocabulary, and the vocabulary needs terms. So entities within the vocabulary are uniquely identified with standard IRIs. What I mentioned earlier, the IRI, which is the identifier. So we have here, for example, for my list of terms, I gave an example for 3 identifiers for the device identifier, an equipment serial number, and balance identifier. So the prefix is AF-R, which means the domain is typically results. So we have here the identifier for equipment serial number, the device identifier, and balance identifier. Those terms are organized in a taxonomy. And a taxonomy is a hierarchical classification, or if you would like to call it organization of terms, that describe a domain. And this is, for example, a domains for results, so AF-R. And we can see the taxonomy, the tree of terms, and we can see that equipment serial number is a subclass of a device identifier, and balance identifier, balance is equipment within the pharma lab. It's a subclass or a child of the parent's device identifier. And if we look at the entire tree, the device identifier is a subtype or subclass of an identifier, and so on. We see the entire taxonomy. So the taxonomy is just the organization of the terms, but now we need to create the relationships between the terms. That's where the ontology coming into play. So there are relationships between the resources. So from this ontology, or from this graph, we can learn that one of the resources has part in another resources, or one of the resources is located in another resources, but more to extend the ontology, you have taxonomy from different domains. So this is for example, an ontology for defining a process within the lab, and this is a taxonomy for defining a result within the lab. So you can see that some kind of equipment serial number is taking place in process within the other ontology. So from the graph, we can learn that a specific equipment within the data instance will be with a certain serial number as context role in a process. An application that looks on the metadata, not on the data itself, just the metadata, the data description layer, can issue a query, retrieve me the list of the equipment ID that took part in a certain process. So now that we understand the terms to achieve interoperability and the ontology, we can start building a model. A model represents one or more use cases. It's a representation of a use case of a technique, and the model uses a RDF graph to describe this technique or use cases. An allotrope standardized model specifically for the pharmaceutical laboratory analytical process is called ADM, Allotrope Data Model. So just for the pharma industry, we define it as ADM. Now, heterogeneous vendor systems can seamlessly exchange ADF file, read, write, and process the data that adhere to an associated standardized ADM. So within the ADF, within the data description, you have the model itself, and the model represents the use case, the ontology, and the terminology, and that's how we achieve a complete interoperability between different vendor systems. So if one vendor sends an ADF file to another vendor system, it can be read and processed, understanding the context of the metadata and the related data cube and data package information. To evaluate the conformance of an ADM data instance, we are using the W3C shackle syntax. Shackle stands for shape constraint language. It's a way to ensure the validation of your RDF graph, your triple store data. We see here an example of one constraint. It's a set of constraints. For example, in any equipment, we have only one serial number. So the constraint, the shape, or ensuring that there is only one serial number is this shape. Equipment serial number must have exactly one value of type string. With one value means the cardinality maximum of one, a minimum of one, so it is exactly one. So the shackle evaluate the conformance of the ADM data instance with a set of conditions which ensure the conformance of the data. So overall, to get an interoperable solution within the pharma, what we saw is a complete solution, a complete framework, all the way from ADF file that's running on the HDF5 infrastructure, and the contextual metadata, which is using the terminology, the ontology, and the model that all encapsulated in an ADF file and with the underlying HDF file format. Thank you very much for your attention.
Thank you, Amnon.